बहुत मैं बीच में आऊँ तभी जाके दिखता है. Okay. So, well, in the last lecture we discussed first fundamental form on a surface. So, the situation that is there in the case of first fundamental form, we considered a surface in parametric representation r equal to r of u1 u2. If you join 2 points p and q over the surface through a curve C, whose equation will look like u1 equal to u1 t, u2 equal to u2 t, means u1 u2 becomes a function of a single parameter t. There are other ways also, but parametric representation of a curve on a surface would look like this. Now, we are interested in finding the distance between p and q along this curve C. So, the distance is given by dr from T p to T q, where dr is the tangent vector to the curve C. So, dr is the tangent vector to C, and if you look at its expression, this will be some r I du I, where I is a dummy index. So, summation is there, and if you want to see dr mod dr, you have to find its magnitude. So, this gives me ds square equal to mod of dr square. This mod of dr square I can write down as dr dot dr, that is r I du I dot r j du j, or in short you can write down r I dot r j du I du j. This is ds square, the distance along the arc p q. So, we fixed up certain notations. R I dot r j was denoted by the symbol g I j. So, du I du j. In the expanded form, this would look like g 1 into du 1 square plus 2 times g 2 du 1 du 2 plus g 2 du 2 whole square, where we have made use of the fact that g 2 is same as g 1. So, it is symmetric in I and j, because it is nothing but the dot product of r I and r j. So, this is called this quadratic form is called the first fundamental form. So, this is how we define the first fundamental form over a surface. So, roughly speaking, this is the distance along some curved line over a surface. All right. Now, these coefficients, we looked into the coefficients of the first fundamental form. So, these coefficients, we worked out certain properties, and we made a matrix of these coefficients. We denoted the matrix of g I j by this symbol. It is a 2 by 2 matrix, g 1 g 2 g 2 g 2. This is the matrix which is symmetric, and if you denote, and what we found that if I denote the determinant of g I j by this symbol g, then this becomes g 1 g 2 minus g 2 square. And we worked out a relationship that this g in fact comes out to be equal to r 1 cross r 2 mod square. This is an important relation, because it tells you that r 1 cross r 2 is non-zero vector on a regular surface, and therefore, this is a non-zero quantity So, if G is if the surface is regular, then the above relation tells you that this will always be strictly positive. In other words, the matrix G I J will be non-singular if and only if the surface is a regular surface. So, this was one of the important observations that we had. All right. So, there are some relationship. For example, the inverse of the matrix G lower I j was denoted by G upper I j's. So, this is the matrix which you denote by G 1 1, G 1 2, G 1 2 and G 2 2. Once G lower 1 2 and G lower 2 1 are same, G upper 1 2 and G upper 1 2 will also be 2 1 will also be same, and this matrix by definition is the inverse of G 1 1, G 1 2, G 1 2, G 2 2 whole to the power minus 1, means the inverse of G lower I j. So, this is how we define the inverse of G lower I j, and the explicit relation between these two matrices is for example, G upper 1 1 from this definition turns out to be G 2 2 upon G. G 2 2 will be equal to G 1 1 over G, and G 1 2 will be equal to minus times G 1 2 over G, and this is same as G 2 1 also. Since they are inverse of each other, we had another relationship that G I k into G k j, this is in fact Kronecker delta I j, whose value we know is 1 0, 1 when I equal to j and 0 when I is different from j. So, these were some of the important observation about the coefficient of the first fundamental form. So, this is what I did in my last lecture. Now, I made use of these things in solving some problems on first fundamental form. So, as an example, this is in fact an example how to compute the first fundamental form over some known surfaces. So, I pick up the surface of revolution because it covers all the conicoids, most of the conicoids. For example, a sphere is a surface of revolution, an ellipsoid is a surface of revolution, a hyperboloid is a surface of revolution. Okay. So, all of them will be taken care of when we discuss surface of revolution. Surface of revolution, the parametric equation is given by x equal to some function of u into cosine v, and y is also a function of u into sine v, and z is a some other function of u. A surface of revolution, roughly speaking, is obtained by revolving a curve around a line. So, if you consider a circle or a semicircle and you revolve it around its diameter, a sphere will be generated. Similarly, if you take a semi ellipse, if you revolve it about its major axis or minor axis, in both the times you will get a ellipsoid. A parabola you take and then you revolve it around its axis, okay. Only one axis is there, you will get a shape of a cup, and that is a paraboloid. Okay. A hyperboloid can be revolved around its major conjugate axis and transverse axis. In the two cases, one if you revolve a hyperbola around this axis, then the hyperboloid of one sheet will be obtained. So, this is a surface of revolution in R theory. You are revolving around this line, which is one of its axes, but if you revolve the hyperbola around this line, then you will get a hyperboloid of two sheets like this. In general, I can consider any curve and I can revolve it around a line, then it will always generate a surface of revolution. Okay. So, one of the surface of revolution is this. So, we will work out the first fundamental form and consequently, we will be working out the coefficient of first fundamental form first. Okay. So, this is the surface of revolution and our job is to compute G lower ij's, G upper ij's and the first fundamental form. Okay, so, what we do? We write down the position vector of a point on our surface of revolution. So, x component here is f u cos v, y is f u sin v and z is a function of u, say h. Okay, G or okay, you can make f g, G is better, okay, f g. All right. Then what are g ij's? G ij's are nothing but the dot product of basic tangent vectors. So, the first of all I will work out the basic tangent vector r 1, which by definition is del r over del u. The two parameters over here are u and v. The first I assume is u and the second parameter is v. So, del r over del u is f dash u into cos v, f dash u into sin v, and this is g dash u. Here dash stands for the derivative with respect to u, that is obvious, and then del r over del v is r 2. So, differentiate r with respect to v will give you minus times f u sin v, f u cos v, and the last component will be 0, because it is simply a function of u. So, r 1 r 2 are determined. So, I can find out r 1 dot r 1, which by definition is g 1 1. So, that can be computed here. So, this is f dash square cos square v plus f dash square sin square v plus g dash square. So, this becomes f dash square plus g dash square. Okay. This is understood that f dash is a function of u, g dash is a function of u. So, it is not necessary to write down all the time u in bracket, that is understood. R 2 dot R 2 by definition is G 2 2, which can be computed here. So, once again f square sin square v plus f square cos square v means simply f square. Okay. Then G 1 2 means R 1 dot R 2. R 1 dot R 2 means I have to consider the product of these two vectors. So, f dash cos v sin v with minus sign, f dash sin v cos v with positive sign cancelled out, and this product of these two is 0. So, G 1 2 is 0. So, you have computed G lower ij's here. Now, I can write down the first fundamental form. So, the first fundamental form, hence the first fundamental form on the surface of revolution is given by ds square, we denote first fundamental form by this symbol, equal to G11, which is f dash square plus g dash square into du square. Since G12 is 0, the middle term of the first fundamental form will be 0. The third term is G22, G22 is f square into dv square, second parameter is v. So, this is the first fundamental form over a surface of revolution. Now, for a sphere, we know what exactly f is. So, if you know in general for first fundamental form for a surface of revolution, you can write down it for a hyperboloid, for a paraboloid, for a sphere and all other surface of revolutions. And now, the next thing was to compute G upper ij's. So, we have developed some relation between G upper ij's and G lower ij's. So, G also I can compute the determinant of G ij's. So, in here it will be simply G11 into G22, because G12 is 0. So, it will turn out to be this much, and this will become G11 is here f dash square plus g dash square into f square. This is G, and now you have to compute all G upper ij's. So, starting from G11, G upper 11 by definition is cofactor of G11 upon determinant of G ij, that is G. So, this is G22 upon G11 into G22. So, this goes off, it is 1 upon G11. If G12 is 0, all the time G11 will turn out to be 1 upon G11. So, 1 upon G11, we know what is G11. So, this becomes simply 1 upon f dash square plus g dash square. G22 in the same manner, it will be 1 upon G22, and this is 1 upon simply f square. G upper 12 will be 0, because G lower 12 is 0. So, these are the G upper ij's. So, this is how we can simply compute all the coefficient of first fundamental form and their G upper ij's and etc. These things are very easy to compute. All right. Now, we can move on to the idea of angle in general between the two arbitrary tangent vectors and the length of tangent vector also. So, tangent vector, now we recognize how to write down a general tangent vector on a surface. We have seen the equation of a tangent plane, and we have also observed that it is generated by the two basic tangent vector r1 and r2. So, if you want to write down a general tangent vector, you write down a linear combination of r1 and r2. So, if A is any tangent vector, so a general tangent vector, a general tangent vector on a surface r equal to r of u1 u2 is given by, let me call the tangent vector as A. So, it will be a linear combination of basic tangent vector r i's. So, a i's are some component, r I are basic tangent vector, I runs from 1 to 2. So, this will be a typical tangent vector on the surface. And if I pick any two tangent vectors, suppose B is another tangent vector. So, if B is another tangent vector, then it will be some component B j into R j. I am using Einstein summation convention all the time. So, summation over I and summation over j are not mentioned, they are understood. Now, if theta is the angle, if theta is the angle between A and B, the two tangent vector A and B, suppose they make an angle theta between them, then cos theta, because these vectors which are tangential to a surface are vector of R3 also, because the entire surface is lying inside R3. So, I can use the dot product in defining the angle between two tangent vectors. Okay. So, this I defined as A dot B upon modulus of A into modulus of B. Okay, this is the formula that we usually use in R3 for computation of angle. So, these vectors lie in R3. So, we are using this formula. So, A is here, it is some A I into R I, B is B j R j upon modulus of A, you can compute from here. Modulus of A, if you compute in the side, so modulus of A square is A dot A. So, A is some A I R I, sorry R I dot again A I A j R j I will write down. So, this becomes A I A j into R I dot R j. R I and R j are vectors. So, dot product will work between them. So, the dot product is G I j to A I A j. So, mod A square is this much, and therefore, mod A will be square root of this. Similarly, mod B can be written down. So, this will be G, we can use I j we are using here. So, I will use L k, K L into A k A L. Okay. And similarly, about B, you will be having G m n into B m to B n. Okay. The numerator can also be simplified. It is G I j into A I B j upon square root of j G k L A k into A L multiplied by G m n B m into B n. So, this becomes the formula for the angle between two tangent vector, where these G I j's are invariant of the surface. So, G I j is not something which belongs to R 3, it is intrinsic to the surface. Okay. So, the angle between them is a function of G I j's and the component of the tangent vector. Okay. All right. Now, we can talk of the tangent between the angle between two curves. That is a special situation. So, first of all we need to understand what exactly we mean by the angle between two curves over a surface. So, assume that there is a surface in parametric representation r equal to r of u1 u2, and suppose there are two curves C1 and C2 which are intersecting each other at certain point P. So, two intersecting curves, what you do, you draw tangents to these curves at the point of intersection. Suppose these are the tangent vector drawn to the curve C1 and C2 at the point of intersection. Now, I have got hold of two tangent vectors. I can compute the angle between them. So, the angle between the two tangents is known as the angle between the two curves. So, this is what we mean by the angle between two curves over a surface. So, the angle between two curves, angle between two curves over a surface. So, as usual I am taking my surface as sigma with parametric representation r equal to r of u1 u2. C1 is a curve given by u1 equal to u1 t and u2 equal to u2 t. So, C1 is obtained by taking u1 u2 as function of a parameter t. C2 is another curve with some other parameter, say u1 equal to some u1 tau and u2 equal to a function of the parameter tau. Okay. Now, let us fix up, because the tangent vector will be dr over dt. So, tangent to C1 at P, P is the point of intersection I have told you. So, is equal to, let us call dr, it will be some Ri dui. I should write down Ri dui upon dt, but that is understood. Okay. Or if you wish, you can write down dr over dt over here and dui upon dt over here. So, this is the tangent vector to C1. Similarly, tangent to the second curve C2, once again at P, it is given by, now the differential is being used all the time with the symbol d. Since we are planning not to mention t or tau, we can understand the differentiation along C1 I will denote by d, and the derivative along C2 I will denote by delta. Okay, so, I do not need to mention t and tau, d and del will tell you on which curve you are moving. So, this is delta r instead of dr. It is not a new thing, it is the same differential. So, this will be some r j and delta u j. Okay. So, you should note down here that d and delta both denote differential operator on C1 and C2, denote the differential operator, or in short differential along C1 and C2 respectively. Okay. So, this is visible, I hope. Okay. Okay, now we are going to work out the formula for angle between the differential between the tangent vector. So, these are the two tangent vectors 1 and 2 on C 1 and C 2. So, the angle theta between the curve C 1 and C 2 is defined as the angle between the tangents, between their tangents dr and delta r at the common point P. So, we have assumed that these two curves intersect at certain point P, otherwise angle will not make any sense. So, cosine theta it should be equal to dr dot delta r upon modulus of dr into modulus of delta r. So, this is what we know about the angle between two tangent vectors. So, I am using the same. So, we will work out what it becomes after simplification. So, r I d u I dot r j delta u j upon modulus of dr. Okay, it will be okay. Let me write down dr itself, and this is delta r. We will compute it. So, the numerator will be g I j d u I into delta u j upon this quantity we have seen, it becomes under root g k l d u k into d u l, and this quantity will be g m n into delta u m delta u n. The same formula, except that the coefficient over there was a k a l b k b m b n. Here they have been replaced by these quantities. Okay. Okay, you leave it here. So, this becomes the formula for the angle between two intersecting curve over a surface. No need of further simplification. All right. Do not get confused that I should cancel out this term from this and this term from this. They will not be cancelled out, because it is a whole series. It is a whole series. This is also a whole series. So, they are in the summation form. All right. Now, if it so happen, okay, leave this expression as it is. Now, we will work out the condition under which the two curves are orthogonal to each other. This is an important condition. This two curves will be orthogonal if this expression becomes equal to 0. Okay. So, the two curves I can write down directly over here, or you can work out from here as well. Okay. So, the two curves C 1 and C 2 are orthogonal if and only if cosine theta is 0. That is equivalent to saying, that is if and only if this box expression becomes 0. So, if and only if g I j into d u I delta u j equal to 0. If this becomes 0, then the curves will be orthogonal to each other. Now, let me write down this in the expanded form, or I can say g 1 d u 1 delta u 1 plus g 2 d u 1 delta u 2 plus d u 2 delta u 1, okay, plus g 2 into d u 2 delta u 2 is equal to 0. Okay, so, this becomes the orthogonality condition. Now, you can further simplify this expression. So, what you do? You divide throughout by d u 2 into delta u 2. So, dividing this expression throughout by d u 2 and delta u 2, it will become g 1 into d u 1 upon d u 2 delta u 1 upon delta u 2 plus g 2 into d u 1 over d u 2 plus d u 2 will be cancelled out, and here d u 2 is cancelled out, delta u 1 upon delta u 2 plus g 2 equal to 0. So, two curves are orthogonal if and only if this condition is satisfied. So, this is the condition for orthogonality. This is the condition for orthogonality of two curves. All right. So, we need to interpret these quantities d u 1 over d u 2 and delta u 1 over delta u 2 geometrically what they are. In fact, what happens if you want to write down the equation of a curve over a surface or in general in R 3, you can have parametric representation as well as you can represent their y coordinates function of x also. Okay. So, in x y plane what you do, if you have certain curve, then its equation is y equal to f x. That means, the x y coordinate along the curve are related to each other with respect to certain function f. And if I compute dy over dx, or you can say f dash x, then this quantity is the slope of the tangent to the curve. So, this gives you the direction of the tangent vector. So, in place of x and y, I have on the surface the coordinates as u 1 u 2. Okay. If you are moving along certain curve, then d u 1 upon d u 2 will give you the direction of the tangent vector. Okay. So, this gives you the direction or slope, whatever you call it. So, these quantities d u 1 upon d u 2 is the direction of the first curve C 1, whereas delta u 1 upon delta u 2 is the direction of the second curve. So, this relation tells me that the two curves are orthogonal to each other if and only if g 1 times the product of the direction plus g 2 times the sum of the direction plus g 2 is 0. Okay. So, what you need to find, if you are looking at the two curves and you want to see whether they are orthogonal or not, you just apply this condition. You just compute the direction of the two curves, put in this formula, if this gives you 0, then the curves are orthogonal. Okay. Huh? Two orthogonal curves. This is the condition for curves to be orthogonal. If curves are orthogonal, they will always satisfy this condition. What is your question exactly? You see the our image, okay? The tangent vector will be orthogonal to each other. That's all. So if you just draw a surface, and suppose I have one curve here, and I can see by my naked eyes if the tangent vectors are perpendicular to each other, then the two curves will be orthogonal. Theta will be pi by 2, and that will lead you to this. Okay? But if the surface is complicated, so you have to see it through GIJs. Next lecture, so we can stop at this point.